Hello, good evening, everyone. Excited for this mathematically intensive session. Okay, so not everyone likes to attend these kind of a bit theoretical, and this is a deep dive. Lot of things which are expected to be known. Okay, for machine learning, deep learning. Okay, especially the mathematical part. So not many people are very keen to get into the mathematics part of it. So first of all, I must congratulate you guys to take such interest in knowing what is really going behind the scenes of these machine learning and deep learning algorithms. Okay. So I think I welcome you all once again. Okay. On behalf of the Analytics Vidhya team, and thank you for inviting me for this DataHour session. I'll try to keep it within the time. Okay. A part of this session is going to be theoretical, and the second part is going to be hands-on. I'll actually show you the optimization in action. Okay. So moving on. So giving a quick overview of what we are going to discuss. Okay. But before that, so these are the four mathematical pillars on which your data science, machine learning, deep learning is standing. Okay. So one is, of course, linear algebra, probability statistics. So anyone who wants to have an expertise in data analytics, especially, okay, business intelligence, data analytics, and business analytics. Okay. So for you guys, probability statistics, hypothesis testing, confidence intervals, those kind of topics are very, very important. For especially the guys who are interested in machine learning, okay, deep learning, data science part of that. Okay. For them, the remaining three topics are very important. Number one is linear algebra, multivariate calculus, that is calculus of multiple variables. Okay. Also called as your matrix calculus. And the last topic is convex optimization. So there are enough resources for linear algebra. You might have already attended enough sessions on linear algebra talking about matrix multiplications and eigenvalues, eigenvectors, norms, the use. I mean, so if you want, if there is a popular demand, I can take a session on linear algebra and its applications as well. Calculus, everyone knows, used in back propagation, gradient descent. So all of these are calculus-based approaches to get the hyperparameters and all. And the last topic that you see here is the convex optimization. So there are two words, one is convex, one is optimization. And I'll demystify both these words, connect with our main topic of interest, and see where all these things are being used. Okay. And why should I bother it? Okay. So quickly going towards the agenda. So these are the 10 points I'm going to cover. Looks too much, but I'll try to be concise, precise. So yes. First thing is, why should I bother about optimization? Okay. And then where else is optimization used in machine learning, deep learning and all? What are convex functions? Because I use that word called as convex optimization. So you need to have a basic understanding of what a convex function is. Okay. And then, yes. Then exactly we need to understand what do you mean by optimization? What are you actually meaning to do? What you are meaning to say and all that, right? And then you want the slides? Yes, absolutely. All yours. Okay. Don't worry. And then there are different types of optimization problems. Okay. And then how do we solve these optimization problems? What are the different approaches? Which approach is better to solve what kind of optimization problem? That is the point number 7. And finally, I'll show you optimization in action using a Python code. Okay. And finally, I'll give you a quick summary of where else is optimization used in machine learning, deep learning. And finally, I'll also talk about some applications of optimization beyond your data science. So that is the agenda for today's session. Yes, warmed up. Let's get started. Any questions? So I have a continuous watch on the chat window. So if there are any questions, please let me know promptly. Okay. Perfect. So starting with why should I bother about machine learning? Sorry, optimization in machine learning. So, okay, here I am expecting the audience to have some decent understanding about machine learning, because I'm not going to lecture on what machine learning is all about, supervised, unsupervised, regression, classification. So if you are familiar with these terms, Can I assume that the audience is familiar slightly with these terms? Because the focus is more on discussing the optimization. I cannot, explain the domain of machine learning in this short span of time, right? Okay, so everyone understands what the features are, attributes. Okay, so features, attributes, different names. Essentially, these will be your columns in our data set. Okay, these are independent variables. And then typically you have one column called as target or the outcome or the labels, different names again. So that is the dependent variable. So the overall task of machine learning is to find the relationship of the independent variables with the dependent variable. Okay, so that is what your machine learning model tries to do. It tries to find out the pattern or the relationship between these independent variables and the dependent variable. That is what the model represents. Okay, so that is what the model tries to understand and express. Fine. So we have the features and the target. So your machine learning model will express the relationship between the features and the target. So let me go ahead and take a simple example. Okay, is the last part visible slightly? Fine. So let's say I've got a small dummy data. I am just taking this small dummy data throughout the discussion. Okay, slightly hidden. Okay, I'll take care of that. Any useful content will not be hidden. Okay, I'll just try to make sure. Okay. So anyway, this equation is coming up in the next slide also. So this data set, it's not a big data set, but essentially I'm going to take this particular problem throughout the session. Okay. So just remember this. So what I've got is a toy data set, and further part of the session will focus on this toy data set so that we can actually implement something. So what I have is a regression problem. You can very well see I have an independent column features. Okay, what we call. So I've got three values, 1, 3, and 5. And the target value to be predicted is 4.8, 12.4, 15.5, a small dummy data or toy data set. Fine. So this is your actual value of y. Y will represent the target variable. So please, keep some of the variables in mind. Okay. So you don't have to keep noting down everything, but if you remember some of these terms, this will help progress in the session. Fine. Okay, so y represents your target variable. Y hat, if you see in the equation below, that represents your model. So I want to do a straight line fit of my data. So your actual data points are represented by these three squares. Can you see three red squares? Okay, so these are the three red squares. I'll just try to highlight them once again. Okay, so this red square is this, another red square, and the red squares. Okay, so these are the actual data points which I have plotted between x and y. And then you have some predictions coming from the model. Okay, so the predictions coming from the model are everything along the straight line, and the original data points are given in the blue circles. Okay, so if you very well see, there is some difference in the predicted value. So which are the predicted values? The predicted values are coming from that red colored line, and the blue circles that you see, that is your original data that I've plotted. So there is some difference. That is your error term, right? So we wanted to predict this. Let's say I wanted to predict this, and what I've got this. So there is a difference here. So similarly here on the right side, I wanted to predict this, but what I got is this. So that vertical difference is your error. Okay, fine. So I've just kept that plot on the right side once again for the reference. So basically, there is, my intention is to find the equation of the best fit line. Simple. My intention is to find the equation of this best fit line, which I'm representing by a red colored line here. And I have also given a very bad fit, a poor fit line, which is represented by a yellow line there. So just for a comparison sake, how a best fit line would look and how a poor fit line would look. Okay. So obviously the line is being represented by this equation y hat equal to w0 plus w1 x or x1, where w0 will represent your intercept and w1 is the slope of this line. So till here everyone is fine. Everyone knows what is regression, so we'll not get into all the details. So yes, so in machine learning, this best fit line is obtained by this algorithm called as linear regression. And these W0 and W1 is also called as model coefficients. Okay, also called as weights. You can also call them as weights or model coefficients. Correct. Epic pen out. Okay, I'll try my best. Fine, because sometimes I need to keep annotating. Okay, I hope this is at one corner. Fine. So as I just now mentioned, we'll be getting some error from the model. So error from the model is nothing but the predicted values from the model. You can see the predicted values from the model. Yeah. So these are my predicted values from the model, and this is your actual value. So predicted value minus the actual value is your error term. Fine. Now my claim is this best fit line will have the minimum error. Simple. A simple claim is my best fit line will have the minimum error for the prediction. Do you guys agree with me? Yes, no, quick. But here the question is, what type of error you are talking about? Okay, so there can be different ways in which you can express this error. Okay, that's another thing which we'll talk about in the next slide. Okay, there could be multiple ways in which I can express this error. Okay, so one of these ways is the mean square error function. One of these ways is mean square error function, MSE. So it is sum of the squares of the error terms and then divided by the total number of data points. That's what this expression says. So you take the sum of the squares of the error terms. That is what this says, sum of the squares of the error terms, and divide by the total number of data points. That becomes the mean. So mean of the square of the error terms, which we call as the mean square error. This is not the only choice. So just for the sake of reference, I'm telling you, there could be multiple choices for your error functions or cost functions or loss functions. Multiple names are there for the same thing. So multiple choices are there. You can use the sum of the error terms. You can use the absolute sum of the error terms. You can use the sum of the squares of the error terms, SSE. I have chosen to go ahead with the mean square error function. And you can also use the root mean square error function. Okay, so multiple ways you can express this error. But the main claim still remains the same, that the best fit line will have the minimum value of this whatsoever defined error function. So you have to narrow down to one error function. Okay, and by default or as a standard practice for regression problems, most of the times we will consider the mean square error as the error function for prediction. Fine. Why mean square error and not the other functions? I mean, that we can discuss sometimes in some other data session. Okay, there is a very interesting analysis why only mean square error and not any other error, but that itself will take another half an hour for me to explain, right? Okay, so how do I define optimization then? Okay, I'll just connect the previous slide with optimization problem. So maximizing or minimizing any quantity is mathematically referred as optimization. So if you remember in the last slide, we wanted to minimize the error. That word minimization is connecting us to the optimization. Okay, so after minimizing, what do you get in hand? The solution. That solution is called as the optimal value. Okay, so I'll explain this a bit more. But before I get to that, let me just quickly give you a quick overview. Supervised learning is of two types. One is regression, one is classification. These are the different algorithms used in regression problems. And then you have again different algorithms used in classification problem. What do you do in regression? We want to find out the equation of the best fit line, as you see here. Okay, we want to find out the equation of the best fit line. Now that can be obtained by a simple linear regression, ridge, lasso, and then elastic net. These are regularized regressions. You can use polynomial regression, random forest, multi-layer perceptrons, ADA boost, gradient boost. I got this picture somewhere from the internet. I just copy pasted here. But yes, these are not the only algorithms. There are many, many more. This is not an exhaustive list. Fine. And in the case of classification, what we are interested is to find the equation or mathematical representation of the separating hyperplane. So how do I separate the two classes? Can you see there are two classes over here? So this is one class and this is another class. So I want to separate those two classes. So I want to get the equation of that separating hyperplane, right? So that is the motivation, that is the intention. This is exactly what you are doing when you say that you are creating a ML model. So what is our ML model doing? Your ML model is trying to express the equation of the best fit line in some format, or your ML model is trying to express this decision boundary in some format, right? So that is what your ML model is trying to do, or DL model is trying to do, correct? That clarity has to be there. Okay, so now we have different loss functions. So what I'm trying to say is, in each of those different algorithms for regression problems, there are different loss functions being used. Okay, so indirectly we have got an idea that all these algorithms are using some sort of a minimization. They are trying to minimize some sort of a loss function. Okay, just like I said that in linear regression, we are going to minimize the mean square error loss function. Similarly, in the case of polynomial regression, you can again minimize the mean square error loss function. In the case of ridge and lasso, you can have the SSC, that is the sum of the squares of the error, plus the penalty term. What is the penalty term? That's basically your lambda times the L1 norm or the L2 norm, the square of the L2 norm, depending on what kind of regularization you are introducing. So for the ridge, you will take the square of the L2 norm, and for the case of lasso, you will take the L1 norm. So there is a penalty term basically, and this overall term, sum of the squares of the error plus the penalty term, that thing gets minimized. So you see, how did I define my minimization problem or optimization problem? You want to minimize something, and what are you minimizing? You are minimizing these loss functions. Is that clear? We are going to minimize these loss functions. For different algorithms, we have different loss functions to be minimized. So the same loss function is not being minimized in all the machine learning algorithms. Is that clear? Okay, I can slightly pause. Okay, so how we are connecting optimization. So what is optimization? Ultimately, optimization means minimizing a quantity. That was the clear definition. If you want, I can go back to that slide. So minimizing or maximizing any quantity is mathematically defined as optimization. So what are we minimizing? What are we minimizing? So that's exactly what I'm trying to convey here. In regression problems, these are the error functions. These are the different error functions which we are minimizing, right? These are the different error functions. So if I can quickly go to, I have a habit of going to the reference pages, sklearn, if you want to go for ridge, RIDGE. So everyone knows this ridge function, right? So I'm just quickly showing you, okay, what it says. You see the main documentation page, the very second line, it tells you there is some minimization going behind the scenes, right? That is what we are doing today. That is what we are learning. What is that minimization happening and why is it that needed, correct? So it clearly tells you this is your SSE term, sum of the squares of the error. And then there is some regularization parameter. Okay, you can call it as alpha, you can call it as lambda, and this is a square of the L2 norm, which is essentially the sum of the squares of the model coefficients. So we'll not get into all the details, but anyone who knows what is ridge and lasso definitely knows what I'm trying to say. Okay, so this entire thing is going to get minimized. Who is going to minimize? How is it going to get minimized? That is what we are going to discuss in the next slide, right? So this is what I just wanted to quickly tell you, that if I just keep on showing you the documentation page for each of these functions, you'll clearly realize that, let me show you sklearn and lasso. Okay. So if you go to lasso, there also you will get. So this is the objective function. And again, we are trying to minimize this loss function. Clearly tells you that we are trying to minimize this loss function. Right? Okay, so there are some questions on the Q&A. Is there any difference between cost function and loss function? So this is the question I'm answering. Is there any difference between cost function and loss function? No, they are all synonymous, different names of the same thing. Like features, attributes, independent variables convey the same thing. Okay, target, output label, they convey the same thing. Similarly, cost function, loss function, objective function, all these three things are same. Dr. Rajita, your question. Why is CNN belonging to regression? See, CNN, I think there was neural network written. It was supposed to be neural network. So just ignore. Okay. So neural networks can be used to solve both regression and classification problems, right? So that is the thing. That is the way we have to take that. Okay. Good. So both the questions are answered. Done and done. Okay. Coming back. I take it this way. I hope that works. Fine. So if you go to the support vector regression page, again, you will get something. Okay. Some sort of a loss function is being used. Okay. Fine. So in the case of decision trees, again, we are taking the sum of the squares of the error. Some optimization is happening everywhere. Okay. So if there are general comments, I may not be able to see them. If there are questions, please try to post it in the Q&A. Okay. So that is where I can take it so that everyone sees what question I'm answering. Okay. So there is one request to everyone. So if you have questions, please try to use the Q&A. Okay. For classification problems, again, logistic regression uses binary cross entropy error. I mean, I'm not going to explain what this is. This is similar to your log loss. Okay. So anyone who knows logistic regression definitely knows what is a binary cross entropy error. That is 1 by n summation minus y log p minus 1 minus y log 1 minus p, something where p is a probability that a data point belongs to the default class, and that probability can be obtained from your sigmoid function. Okay. So in a way, that's a log loss. Simple. Support vector classifier use the hinge loss. I mean, if you go to the documentation page, nowhere it is mentioned, unfortunately, but if you go to the Wikipedia page, you can easily see that your support vector machines use, okay, SVM wiki. You can see that it uses hinge loss. Okay. So first, I'm trying to, convey very clearly that what loss functions are being used, because these are the loss functions or the cost functions which are going to be minimized. Okay. So I'll just search for the word hinge, H-I-N-G-E, and you can see that word here, hinge loss. Okay. So the support vector machines use the hinge loss. Okay. That is the point we are trying to convey. Okay. Fine. So coming back, in deep learning architectures, the good thing is you can create your own loss function and you can customize that loss function depending on the problem that you are solving. Okay. And we have a big list of loss functions available. Okay. We have a huge list of loss functions available in deep learning. So if you want, I can show you for deep learning what all. So I'll go to the keras.io page. Okay. And if you go to that page, go to the API docs. So you will see the list of all loss functions which are available. Okay. So from here, left side, can you see on the left side, losses are mentioned. So I'm clicking on that losses, and these are all the possible loss functions you can customize in your networks. Okay. Deep learning networks, you want to use them. So probabilistic losses are there, regression loss functions are there, classification loss functions are there, hinge loss, Huber loss, log loss, MA, MSE, cosine similarity, KL divergence, binary cross entropy loss, everything, categorical cross entropy and everything, right? So these are all the possible loss functions popularly used in deep learning. Okay. So I think by now everyone has a fair understanding that machine learning algorithms are going to use these loss functions to minimize the error. So what is that error? Unless you minimize the error, you will not get your model. It is as simple as that. You have to minimize some error, and that error function is same as your loss function. Simple. Your error function is same as your loss function. So there is no confusion on that, right? Perfect. Okay, so there are two more questions. Is it same as meta heuristic? I have a slide on heuristic. We'll take that question later. And there is one question by an anonymous attendee. L1 loss cannot be minimized because it is non-differentiable, right? What you said is half correct. They are not minimizable analytically, but you can still minimize using iterative solvers. Okay, so that also I'm going to discuss. Absolutely, taken your point. Okay, so obviously the next question is, can any mathematical function be maximized or minimized? What is your opinion? I'll give a pause here. What do you think? I want your opinion in the chat box. Okay, so what if my function is like this? This is my function. It is monotonously increasing. So think about y is equal to x squared. Okay, so sorry. So y equal to x squared, or think about y is equal to e to the power of x. Do you think they will ever have any minima? These are monotonous functions. So monotonous functions do not have any maxima or minima. So not every function can be maximized or minimized. Okay. So that should be very clear by now. Okay, not every function. That is the reason we are discussing about possible loss functions, because those loss functions should have maxima or minima. That is the important thing. Okay. Okay. So let me further discuss about what a convex function is, and then strictly convex, and then we'll also talk about concave function. So what is a convex function? Any function which has a minima in a given range. Okay, so you can have functions which can have multiple maxima and minima also. So for example, I'll just draw a function here, maybe. So this function has got one minima and another minima. So in this range, there is one minimum. In the another range, there is one more minimum. So this is sort of a convex function, but a strictly convex function will have exactly one minima in the entire range of the x values, right? The one which I have drawn in this slide. Okay, so that is your strictly convex function having exactly one point of minimum. So in machine learning, we prefer to have those kind of strictly convex functions, because if you have multiple maxima and minima, the problem is your algorithm might get stuck in these local maxima and minima, which is what we do not want. So this is a local minima, whereas this is a global minima. Okay, so these are the additional concepts: local minimum and global minimum. So such kind of loss functions are not advisable. So we normally prefer to have strictly convex loss function which has exactly one maxima or minima, right? So in machine learning, we prefer that the loss functions are not just convex but also differentiable. So that was one of the questions raised by one of the attendees here. So yes, we prefer that the loss functions that we are discussing should be differentiable, so that that derivative leads to the point of minima. So what happens to the derivative? At the point of maxima or minima, the derivative will have a, what is the derivative? Derivative is nothing but a slope, right? So the slope of the intercept, okay, at the point of maxima or minima will be 0. The slope of the intercept at the point of maxima or minima will be 0. And that slope can be obtained by differentiating that function. So that is why I talked about differentiability. But as someone pointed that, for example, this is how the plot of the L1 loss function comes out. Simply, that's a line, okay? And that is not strictly differentiable, but still we can minimize that because we have some other ways of solving, right? So we'll see that. So what about non-continuous functions? Those non-continuous functions cannot be even discussed because they are completely illogical. I don't want my model to be built in a way that it is applicable only in certain scenarios. So what is the point in making a model which is only applicable in certain scenarios? Because if the function is, so the model can be built only where the your loss function is continuous. So you don't want to give conditions to your model. So ideally, we will never prefer a loss function which is not even continuous. If it is not differentiable, that problem can be solved. But if it is not even continuous, I would straight away discard that loss function. So such a loss function is most useless. Is that clear, everyone? Fine. Okay, so I'll give you some more examples of the convex functions being applicable to machine learning. Okay. So I have got a lot of questions. Okay, I'll take them one by one. Okay. So it seems people are super excited. Okay. Okay, so some convex functions used in machine learning. So the loss function of your lasso, as we discussed some time back, this loss function, this is how the plot of that loss function mostly looks. Okay, that is your sum of the squares of the error terms, and this is a penalty parameter or the penalty term. Okay, that is a convex function because it does have a minima, but it is not strictly differentiable, but we can still minimize. Whereas the loss function in the case of ridge is differentiable and it is strictly convex. So how does that look? That looks like very simple curve. I'll just clear the drawing. And the loss function in the case of ridge will look like this. A very simple thing. Okay, so okay, good. And then we have the mean square error loss function already we have discussed. In the case of linear regression is also strictly convex. Why is that MSE loss function strictly convex? Can anyone tell me why is that convex function? A very simple question to everyone. Why do you think that MSE is a convex function? Why do you think MSE is a convex function? And I'll give you a hint. So let's see the understanding here. I'll give you a hint. Okay, so look at the formula for MSE loss function. My question is, why do you think MSE is a convex function, first of all? So can you see that it is a 2-degree polynomial? First of all, it's a 2-degree polynomial, and any 2-degree polynomial is a parabola. And the beauty of this parabola is it does have a minima. Okay, right? Once again, I repeat, your mean square error function is a 2-degree polynomial. First of all, you have to understand it's a 2-degree polynomial. You are taking the sum of the squares of the error terms. So it's a 2-degree polynomial. Any 2-degree polynomial in general, ax square plus bx plus c, that formula, okay, will give you a parabola. A 2-degree polynomial will give you a parabola. I'll demonstrate this in the Python code. Just wait, okay? It is there in the next couple of slides. So I'll take a generic equation of a 2-degree polynomial and I'll show you the plot. It comes out as a parabola. So since MSE is a 2-degree polynomial, you can very fairly assume that it is a parabola with a minima. So this is clear. So what is optimization finally, and how is it different from any standard mathematical problem? Okay, so any problem that finally deals with maximizing or minimizing any quantity, that is your optimization. Okay, and okay, so can you see here I have drawn a 2-degree polynomial. It's a 2-degree polynomial, 2x square minus 3x plus 1, and this is the exact plot, and this is a snapshot coming from a Jupyter notebook. Okay, so this is a 2-degree polynomial, and you can very well see there is a minima occurring for this, of course. Now, if I'm asking you find the roots of this polynomial, so what do you mean by the roots? Roots means at which point the polynomial is having, so this f of x is having a value of 0. So those are called as roots. So you can clearly see that this polynomial will have 2 roots. One is at 0.5 and the other is at 1. So this polynomial has got 2 roots. And we know that formula, okay? X equal to minus b plus minus under root b square minus 4ac by 2. That formula we know, right? By which we can calculate the roots of any 2-degree polynomial, okay? Now finding the roots of any 2-degree polynomial is not an optimization problem. Why? Because you are not minimizing or maximizing anything. You are trying to find out, or you are trying to solve this equation. So solving this equation is not equivalent to finding out the minima. So when I say that I am solving an optimization problem, my solution is this and not this or this. Is that clear, everyone? So finding the roots or finding out the points where this function is becoming 0 is not an optimization problem. That is how it is different from any standard mathematical problem. Okay, if I ask you the roots of this polynomial after 1 million years, the answer will still be 0.5 and 1. But if I ask you where is the minima of this function under certain set of conditions, okay, then the value can, I mean, your final answer can keep changing every other day, depending on what conditions I'm imposing. Okay. So that is how, an optimization problem is very different from a standard mathematical problem where you are equating a function of x to 0. You are equating a function of x to 0, and then you are solving for the values of x where the f of x is becoming 0. That's a standard mathematical problem. Mostly you deal with such kind of problems. But in optimization, we are talking about maximizing or minimizing that function. Okay. Perfect. Okay, so this is how the mathematical version of that problem looks actually. Fine. So here we are trying to find the minimum value of the f of x. So you can call it this way. So how do I read this equation? Okay. So listen to me carefully. How do I read this? So find the minimum value of f of x, where f of x is equal to 2x squared minus 3x plus 1. So here your solution would be, listen to me carefully. Here your solution would be the minimum value of the function. So what is the minimum value of the function? Can you see on the y-axis? The minimum value of the function would be somewhere here. That is probably negative 0.125. That is the center point of 0.1 and 0.15. So you'll get somewhere here. So that is the solution to this problem. That is the solution to this problem. Now another type of optimization problem talks about the argument. So how do I read the second problem? So the second problem is read as this. Find the argument x, listen to me carefully, and this is how your machine learning problems are. So your machine learning problems are not of this type. Your machine learning problems, your deep learning problems are of this type, which is why you have to listen to me once. Okay, so find the argument x for which f of x, whatever it might be, find the argument x for which f of x has a minimum value. Find the argument x for which f of x has a minimum value, where f of x will be your actual loss function in the machine learning case, or in the deep learning case. That will be the actual loss function, whatever that be. So this f of x is your loss function or cost function or objective function. And this x becomes a decision variable, that is the generic term. But in machine learning, this x is nothing but your model coefficients, right? So most of your machine learning problems are of the second type, where you are not interested to know the minimum value of the mean square error. Rather, my solution is to find out, my problem is to find out where is this function having a minima. So that is the solution to this problem. Is that clear now? So the solution to the second problem is the point of minima. I'm interested to know where is that minima occurring. The solution to the first problem was this. So these are the two types of optimization problems. The way you formulate them. Okay, perfect. So someone has already posted that x equal to 3 by 4, 0.75. Very good. So what you did was to differentiate that function, equate it to 0. Derivative of that function is 4x minus 3. And once you equate it to 0, means you are saying that the slope at the point of minima will be 0. So the derivative represents the slope. So 4x minus 3 is the derivative. Equate it to 0, solve, you will get x equal to 3 by 4. Absolutely. Thank you. Thank you, Prashant. Okay, I don't want to get into too much mathematical stuff, but the bare minimum things should be still there. So finally, what are the different types of optimization problems? Okay, we have constrained optimization, we have unconstrained optimization. Okay, so unconstrained optimization, one example is the case of linear regression. That is exactly what we have been discussing till now. Okay, so in the case of linear regression, we want to minimize this loss function. What is this loss function? This loss function is your mean square error loss function. So this loss function will be a function of your model coefficients, W. So we want to minimize this mean square error loss function with respect to which variables? Your variables are not X. Your variables are the model coefficients, those slopes and intercepts, right? So how do I read this? How do I read this? So find the model coefficients. These are the arguments. So find the arguments, you can say, or find the model coefficients for which your mean square error loss function is minimized. Given, what is that vertical line representing? Given, and XY is your data. So for a given data, give me the optimal values of the model coefficients where the minimum of the mean square error function occurs. Clear? Where the minimum of the mean square error function occurs. So that is exactly what you are trying to define in the case of a linear regression. Okay. Perfect. The other case is a constraint optimization. So what you are saying is I have just given a simple optimization problem, a dummy one. Okay, right now. So how do I read this? So minimize x1 minus x2 whole square plus x2 minus x1 whole square, whatever. So there are two variables here, subject to some constraints. So what you are saying is these constraints have to be followed. So there can be hard constraints, there can be soft constraints, and there can also be bounds. So depending on the constraints and the bounds, you define something called as feasible region. You define something called as feasible region. And your solution, which is the optimal value, will lie in this region. Okay, what do I mean by that? I'll give you a simple example. So if I go back to my previous slide, this one, if I want, I can introduce one constraint. So here I say, find the minimum value of this function subject to a constraint here that your value of x must be greater than or equal to 0.0 and 0.5. So this is your constraint. You are saying that subject to this constraint. So now whatever constraint you have introduced, as per this constraint, your optimal value of x cannot exceed 0.5. You see, in this case, your solution, the feasible region is this. This is the feasible region. This is the feasible region. Right? This is a feasible region. That's it. So this is no longer your solution. Exactly. This is no longer your solution. Your solution will lie in the feasible region. That is exactly what I was trying to tell you. So every other day you keep changing the constraint, although the main problem is same, but the solution can keep changing depending on what constraints you are imposing. Okay. So now the next question is there a scenario where we get constrained optimization in machine learning? Anyone? Anyone? Is there any machine learning algorithm where we encounter constrained optimization? Anyone? Anyone? Constrained optimization. Lasso Ridge is actually not a case of constraint optimization. Okay. So answer is your support vector machines, SVM. Okay. Okay. Support vector machines. Okay. So I think I had that page open. I'll quickly go to that. So you have the constraints. I can just show you. Okay. Can you see this? Subject to these constraints. So these are the constraints. I'm not going to explain what this. Okay. But you want to find the maximum separating hyperplane. Okay. So you want to find out this hyperplane which has the maximum margin. You want to find the hyperplane which has the maximum margin, but subject to these two constraints. So these are the constraints that you have to satisfy. So this is what you want to minimize. Can you see? You want to minimize this, but subject to this constraint. That is exactly the phrase clearly written in your support vector machines. Okay, so support vector machine is a case of constrained optimization. Clear? So wherever you get subject to means you have imposed a constraint over there. Clear? Now there can be hard constraints, there can be soft constraints. Okay, so hard constraint means that that constraint has to be followed, whatever happens. And there can be conflicting constraints also. And if those conflicting constraints are hard constraints, you may not end up with any solution. So that is why you can, impose a soft constraint also. Okay, or if the data is not linearly separable, then you have to use something called a kernel trick, which is, or you can go with a soft margin variant. So what is a soft margin variant? That is where you are removing the hard constraint. Not exactly removing, but you are allowing for misclassifications. Okay. So we'll not get into other details, but the only takeaway from this slide is, yes, support vector machine is a case of constraint optimization. If you understand that much, understood, right? That is sufficient. So yes, now what are the different approaches to solve optimization problems? There are two big approaches. One is our analytical solution, what we also call as ordinary least squares, and the other is iterative solution. So someone had asked gradient descent somewhere. Okay, so your iterative solutions are your gradient descent. Okay. How to choose which one? So see, all the optimization problems cannot be solved on pen and paper. So theoretical solution is someone solved that problem. You remember someone solved in the chat box by differentiating that function 4x minus 3 equal to 0. Okay, someone solved that problem and you got that optimal value. That is exactly analytical solution. Someone actually solved that, right? 3 by 4. Perfect. That is exactly your analytical solution, which I am referring to, which will give you the exact solution. But the only problem here is not all types of optimization problems can be really solved. Most of the real world problems, the actual business problem, the actual data problems, all the problems that you get on Kaggle, on your different companies, everywhere, they cannot be solved. No analytical solution can exist. Okay. So for that, you need a different approach. And that is where we have the iterative solution. Okay. So this is going to give you an approximate solution, but it can solve all types of optimization problems. That is what I have clearly written over there, right? Okay, before I move ahead, let me take some of the questions from the Q&A. Okay. Okay, we are already short of time. Why the loss function should be continuous? Okay, maybe I'll take that at the end. I try to explain that. Can we have concave function to be used? The concave function, see, the only problem with the concave function is you can have a concave function, no problem. Suppose you want to maximize the profit of a company. So that's a maximization problem, right? But the solvers which are available in Python and commercial solvers, they are hard coded. They are made in a way to solve minimization problem only. That is the only problem. So you have to convert your maximization problem into a minimization one. And how do you do that? How do you do that? That's already done here. If you see, you wanted to maximize this margin. This margin was supposed to be maximized. Can you see somewhere? You want to maximize this margin, right? This margin is given by 2 over norm of W. Somewhere it is mentioned. This margin is given by 2 over. So this is the total margin you want to maximize. But instead of maximizing this, you take the inverse of that function and minimize. So some trick has to be applied. Either you take the negative of that function and minimize, or you take the inverse of that function and minimize. But the point I'm trying to make is all these solvers available on the internet, on all the softwares, commercial solvers, everyone, each and everyone can solve only minimization problem. Okay, so you have to convert a maximization problem into a minimization one. And that's what is done here. Now, do you realize why are we minimizing norm of W instead of maximizing 2 over norm of W? We just took the inverse. So instead of maximizing that quantity, we minimized the inverse of that function, right? Perfect. So that question is also answered. And what else? Would we able to download? I'll give you a link where most of this information is available. Okay, so don't worry. And please, can we get the slides or record? The session is already recorded, so that is already there with you. Fine. So let me go ahead. Okay, we have another 10 slides to cover and a small Python code. Okay, so how do we finally solve? Okay, as I just now mentioned, we have the analytical method, we have the iterative method. Okay, so analytical method is covered in your linear regression class. Everyone knows the linear regression class, right? And the NumPy polyfit function. I'll demonstrate this right away. Okay, and the iterative solutions. What do you do in an iterative solution? You start with some guess value, okay, and keep going downhill. That's what exactly gradient descent does, right? So I'm not going to explain what is gradient descent, but everyone knows what gradient descent is all about, right? So you pick up some, guess value and slightly keep on iterating till you reach downhill, right? That's what the gradient descent tries to do. You are descending downhill. So you start with some guess value and, find out the value of the loss function and then update the weights, okay? And using those updated weight, again, you get the new predictions. So that is your gradient descent. And then you have variants also for that gradient descent, like stochastic gradient descent, mini batch gradient descent, and some advanced gradient descent techniques are also there. which are used in deep learning. Let me show you that. So if I go to this link called as optimizers. So what is an optimizer? Quickly, what is an optimizer? Common sense now. Everyone should be able to answer this. What is an optimizer? So optimizer is the algorithm which is solving the minimization problem. Optimizer is the algorithm which is finding the minima. That is an optimizer, right? So the scikit-learn API refers to this by the name as solver. Remember, so we have different names again. So scikit-learn refers to this as solver. The SciPy API refers to this as a solver. But the Keras in deep learning, we refer this by the name as optimizer. Okay, so optimizers. So I can just quickly show you. These are all the available optimizers. But what are these functions trying to do? They are again some variant of your gradient descent. SGD is your stochastic gradient descent again. ADAM is adaptive momentum, adaptive delta, adagrad, adaptive gradient, that is ADAMAX, NEDAM, that is Nesterov adaptive gradient descent again, and then many more are there, right? So these are all variants of your same gradient descent, but a bit more advanced because they have the momentum terms and they are adaptive. Okay, so these are all different algorithms, which of course I'm not going to get into all the details, but moral of the story is while you are training your neural networks, you are trying to minimize some MSE loss function or binary cross entropy loss function or categorical cross entropy loss function. Some loss function you would have taken while defining the neural network and compiling. You remember, anyone remembers? During the compilation step, you are defining this optimizer, right? So exactly. Okay, coming back. Okay. You have some heuristic solvers and meta-heuristic solvers again. So like genetic algorithms, which are evolutionary algorithms based, particle swarm optimization, ant colony, simulated annealing. So anyway, maybe we can have a separate session on these heuristic solvers, which are actually very, very interesting, and they really solve a lot of industry problems. Okay. In SciPy, we have the Nelder, Mead, Powell, LBFGS is limited memory, Broaden, Fletcher, Goldfarb, Shannon algorithm. SAG is a stochastic average gradient descent and all that. So I'll quickly do a quick demo and then we are good to go. Okay. Fine. So I'll take another 5-7 minutes. Will that be okay? The moderator, 5 to 10 minutes, not more than
yes,
that.
Yes, sir. Fine.
Yeah.
We are, yeah.
Yes, because anyway, we started 10 minutes late, so I'm counting my time. Okay, thank you.
Yes, sir. Yes, sir.
Yeah. Okay, because I don't want to skip the last 7-8 slides, which is the most important. Okay, because there I am discussing the real application part, the workaround. Okay, good. Thank you. So now that we know that we have so many solvers, and these are the two approaches. Okay, now the question here is, I have, okay, let me show you one more page before I go ahead. Let me show you one more page. SciPy.optimize.minimize. Let me show you this page. Very interesting page. So all the optimization routines, whatever I mentioned in my last slide, are present here. Okay, and most of the machine learning algorithms are calling this function behind the scenes. You may not realize this. Even the logistic regression, let me show you the logistic regression. Okay, even the logistic regression of the scikit-learn does this. So it does have the solver. I'll just show you. So can you see this solver option, LBFGS? Where is this LBFGS coming from? I'll show you. This LBFGS is coming from here. LBFGS, limited memory, Broaden, Fletcher, Goldfarb, Shannon algorithm. Okay, so now in this page, you will get all the list of solvers available for machine learning. So these are all the solvers. And if you go down here in the logistic regression page, you have the choice of all these solvers. The Newton's conjugate gradient, LBFGS, live-linear, SAG, Saga, and all that. Okay. So you are only specifying, but where are these actually hard-coded? Where are these coming from? They're coming from this function. So this function is being used behind the scenes. So again, what do you see? Logistic regression, the simplest ML or statistical algorithm that you have been knowing for classification, is also using optimization behind the scenes. You see? Now, further, the documentation page is very good. Actually, you should actually read the documentation. Have a habit of reading documentation. This clearly tells you that these are the algorithms available for unconstrained optimization. So you can use the conjugate gradient. You can use the BFGS method. You can use the Newton's conjugate gradient, dogleg, trust regions, Newton's conjugate gradient, Krylov method, and so many. And then you have the bounded and constrained minimization. So that is where you can use the Nelder-Mead, which uses the simplex algorithm. You can use LBFGS. You can use the Powell's method and so on. And for other kind of constraint optimization, you can use your SLSQP also. That is a sequential least squares quadratic programming, Kobila and all that. So this solves majority of your problem. Which algorithm to use for what kind of problems is partly solved because it is very clearly mentioned what to use when. And if you're still struggling for the case of logistic regression, it is very clearly mentioned that all different solvers don't support penalty. So if you are deciding that I have to go for L1 penalty, then your choice is limited. Annual penalty is supported only by liblinear and Saga. If you are going for L2 penalty, which is the default, then you can select any of these. So the default penalty is L2 if you see. And there is very clearly mentioned here, regularization has been applied by default. What regularization? L2 regularization is already applied by default here. Okay, so which means we have to use LBFGS. So if you want to apply L1 penalty, then you have to change the solver because LBFGS does not support L1 penalty. So the choice of the solver depends on many things. Number one, it depends on what kind of constraint you have. Okay, whether do you have a constraint altogether or not, whether it is a linear constraint, non-linear constraint, whether you have an equality constraint, inequality constraint. Okay, and then whether what type of regularization you want to use, that also determines what kind of solver you want to use. Yeah, does that give you a fair enough idea now? Is optimization a part of tuning? Yes, I do have one comment in one of the slides about hyperparameter tuning, which also involves optimization. Absolutely, absolutely. So coming back to this problem, okay, I'll just go back to, so what I did was, this is my MSE loss function. This is my MSE loss function, and y hat, I had defined it to be a W0 plus W1x. So if I substitute, listen to me carefully, if I substitute this y hat in this expression, then the total loss function looks like this. The net loss function looks like this. This is a net loss function. Okay, after I substitute, can you see? Yeah, can you see? This is your y hat. Now clearly what I want to conclude from here, listen to me carefully. What do I want to conclude? Your net loss function is not a function of your features. Your features is your data. Data is constant. The loss function is not a function of your y. The loss function is a function of your model coefficients. These are the actual variables, and that is why I said your loss function is a function of your model coefficients, which are the actual variables. X and Y is your data, my dear. X and Y is your data, and data is constant. You can't change the data to fit a line, a hypothetical line, right? You have to change the line to fit the data. So please understand, X and Y is your data. Data is always a constant. So what is the actual variable in this? The actual variable is your model coefficients. That is why your loss function is a function of model coefficients. Now that is clear. So what did I do? I plotted my loss function with respect to the model coefficients. Okay, I plotted my loss function with respect to the model coefficients, right? And then when you solve all that, this is the final thing that I get. Okay, so how do I use this equation? I have one slide where I am actually going to use this equation. This was my dummy data, and I just plug in the values. So what is xy bar? Xy bar is basically the mean of xy values. X bar into y bar, that is the product of the mean of x values and the y values. Then the denominator term here. is the mean of the square values of x, and the other term is the square of the mean. So if I just plug in the values, I'll get some optimal values. You can see 2.67 and 2.88. Okay. So let me switch to the Python code. Okay. And demonstrate this. Okay. So first, I've just taken the same thing, same 3 data points as a NumPy array. Can you see? I've taken my data points X and Y. Powerful session. Thank you, John. Okay. So this is my data points. I've taken as a NumPy array, and what I'm doing is a simple polynomial fitting. So this polyfit function can fit a one-dimensional data, only one-dimensional data, please remember. And after that, it will return you the polynomial coefficients. I'm converting those polynomial coefficients into a polynomial object, which I can evaluate later. Fine. So can you see 2.675, 2.875? Can I go back to the code? Slide. 2.67 and 2.88. Perfect. It matches. Exactly. It matches. What does that mean? This is the exact equation being used by this function. This is the exact equation. I'm telling you the exact equation being used. Most people don't know what is being used behind what equation. Okay. Let me ask you. So most of the time people think that in linear regression, gradient descent is used. I can tell you that is absolute nonsense. Linear regression does not use gradient descent, my dear. It uses ordinary least squares. And if you're still wondering why am I learning all this, I'll just show you quickly. Do I have the linear regression page? No. Okay, I'll just show you the linear regression page. And unfortunately, there is no details. There is no equation. It only tells you I am using ordinary least squares, and people have literally no idea. Literally, people have no idea what is OLS. Nowhere in this entire page, any expression, any equation for OLS is there. There is no expression for OLS in the entire scikit-learn API, because the creators of this API assume that you guys know what is OLS. Okay, this could be a bit contradictory, I mean, ironical. Okay, unfortunately, they assume that you know what is OLS. Okay, whereas most people don't even know what is optimization. Forget about knowing even OLS. Okay, and still many people I encounter even today, they think that linear regression uses gradient descent. Absolute nonsense. It cannot be more wrong than that. Okay, so if you're still wondering why am I giving these equations, that is the equation used behind the scenes. Right? Perfect. Okay, before I go to the last slide, I'll go back to my Python code once again. So you see that this is the polynomial coefficients I used. And then I'm using the linear regression class from your scikit-learn. This is a X and Y once again. Okay, I am doing the model fit. Everyone knows this, right? And see the intercept is 2.875 and 2.6. Perfect. The same values what I got from here. 2.675, 2.875. So what is the moral of the story here? Moral of the story is my linear regression actually uses ordinary least squares. And what is the expression for the ordinary least squares? My dear, this is the expression. Convinced, everyone? Okay. Fine. So we are almost nearing completion. But before I do that, I'll give you some more applications. So let me go with that function. So I want to minimize that function. Which function? 2x squared minus 3x plus 1. The same function which I used in my slides. The same function. Remember, someone had already solved 0.75. Now I'm going to solve for you that same expression. So what I defined is a lambda expression, the same function which I want to minimize. Then from scipy.optimize import minimize. Do you see I'm using the same function? So it's not just theory. I am doing the practical now. So this was the same web page. I'm using that same function now. So you are minimizing this function with some guess value. So what is x naught here? You have to provide some rough guess where the minima lies. Okay, and this can be obtained from the plot. We had seen this from the plot. We got a graph value at 0.7 something, right? See the solution here, absolutely. 0.7499999. And what did I tell you sometime back? That these are iterative solvers and they will only give you approximate solution. Did you notice? And that is the reason you do not have the answer as 0.75. Is that clear? That is the reason, if you are still wondering and pondering, why is my answer not 0.75? Because I have already declared that. These are iterative solvers. How many iterations did it take, my dear? 2 iterations. How many times the function was evaluated? 6 times the function was evaluated. Okay. Number of Jacobians. Jacobians are nothing but derivatives. So 3 times the function was differentiated. Okay. And this is the minimum value of the function. What is Hessian? This is the double derivative of the function. You need the double derivative to prove that the value that you have got is indeed a point of minima. So let me go back to high school mathematics. So the first derivative will tell you the point of maxima or minima. That's what everyone knows. But the second derivative of the function will tell you whether that point is indeed a maxima or minima, right? So if you evaluate the second derivative at the point of maxima or minima, and if you get a positive number, it relates to a minima. And if you get a negative number, you get a maxima. So going back to that function, if you double differentiate, what do you get? 4, right? If you double differentiate this function, you'll get 4. What is the first derivative? 4x minus 3. The first derivative is 4x minus 3. So the double derivative is only 4. And what is the inverse of that 4? What is the inverse of that 4? 0.25. Exactly. And that is positive. So what is Hessian? Hessian is nothing but your double derivative. And what scikit-learn is printing is the inverse of that. So 1 is 1 upon 4, 0.5. And that is positive. So indeed, we know that we are talking about a minima. Indeed, we are talking about a minima. Okay. Finally, there is one more quantity called as Jacobian. So this is your value of the function, value of your derivative. This is the value of your derivative at the point of proposed minima or hypothesized minima. At this minima, what is the value of the derivative? And this is the value of the derivative. Can you see? The value of the derivative represents the slope, and the slope is fairly close to 0. Not exactly 0, but fairly close to 0. Is that clear? So Jacobian represents the slope. Basically, Jacobian represents the slope at the point of maxima or minima. So the slope is nothing but the derivative. So Jacobian is the derivative. The final Jacobian is your derivative of your function at the point of maxima or minima, right? And that is supposed to be close to 0 within some tolerance. There is some tolerance. I don't want to go into all that, but there is some tolerance. If you see, there is some tolerance also. There is some tolerance. Okay, there is some default value of that tolerance. So depending on what tolerance you are imposing, okay, this value can increase or decrease. Okay. So moral of the story, this tells you that our derivative is fairly close to 0, which means this solution is reliable. Okay, any question? So what is the function value telling you? Function value is telling you what is the value of the function. This is, if you're talking about the mean square error function, this will be the minimum value of the function. What is the minimum value of the function? So this is the minimum value of the function, negative 0.125 on the y-axis, and on the x-axis it is 0.75. Is that clear now? On the x-axis it is 0.75. That is the location of the minima. That is the location of the minima, and the value of the function at the point of minima is negative 0.125. Perfect. Okay, so there is, if you want, you can change the method. If you want, you can change the method. Okay, and in this case, what happened? If you change the method, I did get 0.75 in this case. Very interesting. Okay, I'll not get into all the explanations, but this time the function took 24 iterations. So it's up to you. In just 2 iterations, you got very, very close, or do you want to go to 24 iterations and actually reach the point of minima? So depending on all these different techniques, you can just try them. Okay. So you can just try each of these techniques and see what values you get. Okay. Okay. So let me just take up the last 2 slides and we are good to go. Okay. So I've already discussed about this. These are the other solvers. Discussed about this. Okay. So where else? I think I've fairly given you a good idea. Okay. I don't want to repeat this. Support vector machines, deep learning, hyperparameter. So someone had this question. So yes, indeed, the hyperparameters can be optimized by the concept of optimization again. Now, whether you're talking the hyperparameters of a machine learning algorithm, like suppose for support vector machine, you want to go with what type of kernel? You have different choice of kernel, linear, RBF, polynomial kernel, sigmoid kernel. You can optimize the kernel. Or if you want to go with a polynomial, then you want to optimize the polynomial degree. You want to optimize the value of C, that is your regularization parameter, or you want to optimize the value of gamma. That influences the amount of influence each data point will have on the decision boundary, right? That is what the gamma conveys. So each of these hyperparameters for every machine learning algorithm can be optimized by using some techniques. So normally we use grid search, right? So what are the other applications? Now this is where I am falling short of time. So what I'll give you is, because of the interest of time, I'll give you a link. Okay? And in that link, I have given at least 30 applications of optimization which are not machine learning based. Will that be okay? Instead of me explaining each of them? Guys, yes, can I do that? Perfect. So if that works, then I think I can. Just a minute. I'll give you a link of that. And then we can wind up. I'm almost done. That's the last slide anyway. Okay. So if you go to the Analytics Vidhya blog web page, this is the main web page. Let me share this link with you. Okay. With everyone. And if you see this article, this summarizes everything, including the code, everything. Whatever I have discussed today is all there. So you don't need my slides at all. All the slides have been created from here. Everything in detail is very neatly, nicely explained, written by me and published today for you guys, especially just because I wanted to take this session. I wrote this article for you people. Okay, thank you for your time. And as I said, all the codes are there. You can copy paste the code and try it by yourself. So whatever the code that I've been running is also there. Where else is optimization used? I have given you at least 24 applications, right? So I'll give you the link for this article. Please go through this. It's all yours. Download this article and please make use of this. So everything, you don't need my slide anymore. It's all there, okay? So I'll just paste the link for this article on the chat box. Please mark this, bookmark this, okay? So it's all yours, it's all yours. Finally, these are some commercial solvers which are also mentioned in that article. And this is my final slide. Thank you so much for your time. Let me take a couple of questions, okay?
Hello,
and yes, you can scan that code. That will directly take you to my LinkedIn page. You can use your mobile's scanner. I mean, the LinkedIn app has got a scanner. You can use that LinkedIn app scanner. Connect with me, okay? So.
Hello, Prashant.
Yes.
Before we proceed to answer your questions, I would like to request the attendees to please fill in the poll about feedback, as it helps us to conduct more such sessions.
Okay. So we have people 10% from Africa, another 10% from Europe, 70% are from Asia, but we do have participants from North America and South America as well. So none from Australia. So that is the result for the poll. Thank you. And the other question was on the feedback. Okay, so most of the people have 0 to 3 years of experience, 65%. Good, which is good. And another feedback has, poll has come up. Please, I request everyone, all the remaining 81 participants to give a feedback. Okay. I'm waiting, and then I'll take some 3 questions are still pending in the Q&A. So if you guys are still there, I'm ready to answer those 3 more questions. Okay. So most of these questions are actually answered somewhere in this article, but definitely if you think still there is a need for a discussion, I'm still there.
Yes, we can continue.
Yeah, thank you. So 1 or 2 questions I'll take, and any book recommendations? Absolutely, a very good question. And please allow me. This is one super book I would recommend everyone to follow. This book by Professor Singareshu S. Rao on engineering optimization. This you can easily get on Amazon. Okay, a Wiley publication. Indian audience can easily get this book. Okay, Indian audience especially. Okay, most of the optimization courses conducted in top tier 1 institutes like IITs and NITs use this book as a textbook. Fine. For the international audience, I would like to suggest another book by Edgar and Himmelblom. Okay, EDGAR HIMMEL Edgar and Himmelblom. That is one of the standard textbook across most of the universities across this planet Earth. I'm not aware of the optimization books being followed on the planet Mars, but at least on this planet, any course on optimization cannot be complete without following this book on Edgar and Himmelblom. Okay, where is this book not coming up? I'm sorry. Let me do a Google search. Edgar and Himmelblom. EDGAR HIMMELBLAU and optimization. So the name of the book is Optimization of Chemical Processes. Okay. Although the name says it is specifically for chemical processes, but the first 20 chapters are absolutely awesome. Okay, they are pretty generic. Okay, so yes, you can easily get the PDF. This is the name of the book. Okay, Optimization of Chemical Processes by Thomas Edgar and David Himmelblom. Okay, I probably misspelled. So this is one where you will easily get this book in your libraries if you're coming from academic background. Okay. Otherwise, you can also catch hold of the other book by Singareshu S. Rao, S.S. Rao. S.S. Rao, just search S.S. Rao in optimization. You will easily get that book. Okay, so these are absolute beauty. Okay, fantastic books to follow. So that answers the question. Done. Kindly share the book name. Yes, this is the book. I have just answered that, Shashi. And should I try to optimize coefficients to get optimization? See, anyway, your machine learning algorithm is doing that for you. Okay, Fatima, that is what the machine learning algorithm is already doing for you. So you do not have to explicitly break your head with these minimizers unless you have a physical problem that you are trying to solve. So some of these physical problems I have already conveyed in that article. If you go to my article, some of these physical problems I have very clearly discussed. Okay, so if you are facing some of these physical problems, okay, let's say you want to minimize the cost of the manufacturing a product. So you can express that cost in the form of a manpower cost, raw material cost, inventory cost, transportation cost, logic. So once you have all the numbers, you can make a mathematical expression and want to minimize that. For that, you will have to use the minimizer. So I have already shown you scipy.minimize function, right? So that is what people are doing. Otherwise, if your problem is just too complex, you can make use of some of these commercial solvers. And especially I should mention about OR tools. This is a Google's product, which is open source. Okay. So fantastic optimization tool is this. So that is also, thank you, Lena. Thank you so much. Lena had already asked one question. Why should the loss function be continuous? I have already answered, I think. And there is one last question. Is it the same as meta? See, optimizations have many formats: heuristic, meta heuristic, and these are the straightforward optimizations. So I mean, there are multiple application areas. So everywhere you will not get the same standard optimizations. Okay. So I have tried to summarize what are the cases of straightforward optimizations, but there are cases where you would indeed use genetic algorithms, simulated annealing. Let's say some part of my PhD thesis also I have used genetic algorithms and simulated annealing and particle swarm optimization. Okay. Perfect. So follow this article. It has all the things that we have done for the day. And thank you so much.